So day 2 of pre-calculus and honors pre-calculus, we're doing some review for functions. Begin with relations. A set of ordered pairs can be expressed as table, mapping, graph, or different equation forms. Once we have a relation of values or numbers, we can look at the domain and the range. The domain is the set of all x values. And the range is the set of all y values. So now we're being asked to give the domain and range of each relation. When we express sets of numbers, there are different formats we can use. Because these are discrete points, they're individual numbers, it really only makes sense for us to use what's called set notation. It begins with a squiggly bracket on both sides. And for the domain, we're going to list the values incrementally from smallest to largest. So I'll start with -5, -1, 3, and 7. For my range, similarly, I'll use my squiggly brackets, and I'll start with the smallest value. And even though -1 shows up multiple times, I'm not going to list it multiple times. And I go from smallest to largest. What's my smallest x value in this domain? Like -3. And then I've got a value at -1. Got two values at 1, but again, I only list that once, and a value at 2. Now I'm going to look at my ranges. I don't really correspond them to make ordered pairs. I'm just looking at my smallest y value and then working on my way more positive. What's my smallest y value? -4, -3, 0, 2, 2, 3, 4, 5. When I'm looking at a relation that has something more continuous, something that can graph, I can either express it in set notation, which is a lot like this, or I can express it in something called interval notation. So let's begin over here on the left. I've set up an opportunity to show these two different formats. Picture this as a number line which has been shaded. And if I want to express this relation as set notation, the true formal way to do it would be to start my set notation, squiggly bracket, and say that the value begins at a -4, and all my values are greater than that or equal to that. In other words, x is trapped between -4 and 3. Why did I not put a line under this? Because it's an open circle. It's not equal to that. Or x is greater than or equal to 5. So x is trapped between the values of -4 inclusive and 3, or x could be a value greater than 5 or equal to 5. Interval notation is similar, slightly different scenario. I'm going to look at this interval and find the endpoints. It goes from -4 to 3. Do I want to include the value -4? I do. So the way we include it is by putting a hard bracket. And the way we exclude it is by leaving a parentheses. And that says it's the interval from -4 inclusive up to but not including 3. And then when we want to express that we want the union between that and the other piece, not the intersection, but the union. And now to do this, we start on the left from 5. And what's the biggest number to the right? Infinity. So we draw the infinity symbol, sideways 8. And 5, do we want it to be a hard bracket or a soft bracket? Hard bracket, because we want to include the number 5. What about infinity? Almost. We want to make it a soft bracket because infinity is truly not a number. It's actually a concept. It's the biggest number possible. It's not actually a value, so I can't put a hard bracket there because you'll never reach it. How many of you have not experienced interval notation before? Almost all of you. Okay. How many of you have experienced set notation or some form of this before? Okay, most of you. We're going to typically use mostly interval notation. It's more efficient when you're describing intervals. But when you're describing discrete points, you'll want to use set notation. So here I'm giving you an opportunity to try both of them. Let's first do it with set notation. When we're talking about domain, since we're only talking about the x values, the best way to say it is x with a little bar there, which is described or translated as such that. And now what do we want the x solutions to be? What does this domain entail? Are these arrows down here? So they mean that the function continues forever and ever and ever, which means this will include all x values. So what I could say here is that x is an element of, it's a C with a little line making it look like an E, real numbers. And by putting a second R on there, we're saying it's not just, or second line on the R, it's not just an R, it stands for the concept of all the real numbers. What about the range? Well, we're still going to use set notation, but instead of x such that, what should I put here? Well, because I'm trying to make sure we all know how to won't. She said why, and I explained why instead of okay. So then, what are we going to do here? What are the range values? It goes up to 1, 2, 3, 4, 5, 6. So we can easily express it as y is less than or equal to 6. Y such that y incorporates the values less than or equal to 6. What about writing those same relationships in interval notation? When we want to do real numbers, I'm going to go the far leftmost point, negative infinity, comma, the far rightmost point, positive infinity, and then should I include hard brackets or soft brackets? Good, soft, because infinity isn't a real number. What about for the range? What's my lowest range value? Negative infinity. What's my highest range value? 6. Should this be a soft or a hard bracket? Soft for infinity. What about the 6? Good. Okay, once you guys try number 5 now yourselves, please, do set and interval notation. Yeah. Domain is left and right. X values. Range is up and down.
But you have to do it
I think that's an arrow, doesn't it? Looks to me like it's approaching the x-axis asymptotically. Asymptotically, it's getting really, really close to it, but never quite reaching it. I'm definitely making an assessment there that's not explicit in the picture. All right, please take a look and see what you think. Any questions on that? Yeah.
Why would it be 0 for the range for 4?
Instead of going on up forever? Yeah. You could justify that it goes on up forever. To me, it looks like this is asymptotic. It's approaching this line and it's never going to quite reach it. But I don't think, I think you could argue that it's not. It's going up forever. I'd be okay with that. Okay. Back at page 2. Determine the domain and range of the following relations. How do I know what this domain might be just from looking at it? It could be -5. If x were 0, that's true. So let's take a look at this. This part, x squared. What's the smallest this could be? Do you agree it cannot be a negative number? What's the largest it could be? Positive infinity. So overall, this function can go from a value of -5 up to infinity, right? That's what the range of this function could be. And what x values might be allowed? Could I put a negative number in here for x? Could I put a positive number in here for x? Is there anything that I'm not allowed to put in here for x? Is my domain restricted in any way? It's not. Therefore, I can say from -infinity to positive infinity. It's all real numbers available for x. Now, when do I have to concern myself with a domain from an equation or a relation? One is when it's a square root. Could I put an x value of 4 in here? Sure, 4 minus 2 is 2. It gives me the square root of 2. That's a valid answer. Can I put an x value of 2 in here? 2 minus 2 is 0. What times itself is equal to 0? 0. So that works. Can I put an x value of 1 in here? No, because that gives me a negative number. So in other words, what I need to do is ensure that this thing on the inside, x minus 2, has to be greater than or equal to 0, don't I? The argument inside here has to be greater than or equal to 0. Now I can just solve this and say that means x is greater than or equal to 2. That's my domain. So for my domain, if I'm using interval notation, I'm going to simply say it's going from 2 up to infinity, equaling as well. And what about my range? Could this whole function ever reach a negative number? No. Could it achieve 0? Yes. Could it be any number bigger than that? Yes. Therefore, I expect this is going to be from 0 up to infinity. It could equal 0. Okay. Let's take a look at the functions. A function is a special type of relation in which each element of the domain is paired with exactly one element of the range. In other words, when you plug in an x value, you're confident that you're going to get exactly one y value back. So when I plug in -3 throughout this whole relation, do I always get the value of -4? Yep. 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 All these x values, even if they're duplicated, give me the same y value. So this, yes, is a function. But here, number 14, if I plug in an x value of -9, it's unreliable as to what y value I'll get. Therefore, is this a function? No. Over here, I've got the 2 showing up twice. I've got the 8 showing up twice. So is this a function? It is. Because if the x value is -7, I could get a y value of 2. It's okay that I could possibly get 2 different y values, 2 different x values for the same y value, because that would be like a parabola, which is still a function. What you're looking for is the x repeating. Since these x's are not repeating, give me different values. This is, yes, a function. And all this is another way of doing what we remember as the vertical line test. Remember that? It's where you take a vertical line and you drag it across the graph, and you see if at any point it touches more than one part of the graph. If it doesn't, you can say, yes, it's a function. But here's an example where when we drag it across the graph, we see places where it reaches the graph, touching it in 2 places. That doesn't work for a function, so we say no, not a function. I'll let you work on this last one. When we're talking about functions, we're going to have notation formats. You might remember something like this, y equals 3x squared plus 5. Hopefully that looks familiar to you. What would it look like if we were doing it in function notation? All it means is we're swapping out y. Come on, guys, stick with me here, please. You're going to have plenty of time to go back and do the ones I leave blank for you. I'm swapping out the y with f of x. This is pronounced as f of x. And this has some value to it. One way it has value is I could have multiple expressions, f of x and g of x, and I can refer to them by their name like that. The other value is that if I were to say something like g of 3, what am I saying? Plug 3 in for x and give me the value of that function. So down here, when we say evaluate the function for f of -5, that means f of -5 takes this same expression, but instead of it being x squared, I'm going to put -5 in for x. It's -5 squared. Instead of -6x, I'm going to put -6 times -5 plus 23. Now, I'm aware that you are the generation of AI, photo math, and Google to do my homework for me. I want to see your work. I know you could plug this in really quickly, and you can probably do it in your head, but you need to show me your work so I know it's you doing it, please. 25 plus 30 plus 23, 55 plus 23 is 78. Any questions on evaluating functions? Okay, last page. X and Y intercepts. Intercepts are points where a graph intersects the X or Y axis. An x-intercept occurs where y equals what? 0, good. And the y-intercept occurs where x equals 0. And a function can have 0 or more x-intercepts. Remember, in your polynomials, you might have a 5th-degree polynomial, or it could have 5 x-intercepts, but it'll always have at most 1 y-intercept. I recognize that you're going to be guessing at some of these things, what their exact values are. But if we're looking for the x-intercept of this one, what would you say it is? 4. I'd like to see that written as 4 comma 0 because it is a coordinate. What would be the y-intercept? 0 comma 2. All right, so what are zeros? They're the values or points that make the function equal 0. Now, there's always a struggle over roots, zeros, and x-intercepts. How are they the same? How are they different? I like to think that if we've got like tell me about this function. Set y to 0. Okay, so we could talk about the x-intercepts, right? And say, what would it take to find the x-intercepts? Well, those are coordinates where the y value is equal to 0. And in this case, if you did that, you'd get 0 is equal to x minus 2 times x plus 3. And you'd apply this zero product property to say two things multiplied together to make 0, mean that either x minus 2 equals 0 or x plus 3 is equal to 0. So x is 2 or x is negative 3. The x-intercept then would be officially 2, 0 and negative 3, 0. If I asked for the zeros of the function, what I'm saying is what values make this function equal to 0? So you could either say x equals 2, negative 3, or you could, again, say the whole value. I like this kind of better because at this point, there is no y value, right? The 0 of the equation suggests that you've already set it equal to 0. And if you were asked for roots, that's when you'd say x minus 2 and x plus 3. It's the factors that produce the zeros or the x-intercepts. So there's always a little frustration of knowing which one is which. And I think different teachers ask for different things. Ideally, x-intercept should be expressed as a coordinate pair. Zeros can be expressed either as numbers or as a coordinate pair, and roots should be the factors. Okay, to find zeros, what do? How do you find the zeros of a function? Yeah, set f of x, the whole function equal to 0 and solve for x. To find the y-intercepts, what do? Exactly. Find what the function is when you put 0 in for x. Okay, last piece of the notes today, we're going to talk about some critical points in a polynomial graph. Critical points are points in the graph that changes either its direction or its shape. And by that, I mean its slope, its tendency to change. Extrema are points where the graph changes direction. So for example, the function was getting more and more and more. It reached a maximum value, and then it turned and began to get less. So this is called a maximum. And there's two types of maximums. A point with the greatest value compared to the points around it is called either a local maximum or a relative maximum. A relative or local maximum. If in fact our function is achieving some maximum value and never gets any higher, this is the highest value of the entire function, that would be called an absolute maximum. And you'd expect to see that in something like this, like an upside down fourth degree function, where it has a maximum value and the function itself never achieves higher than that. Similarly, if you have a minimum value that may be smaller elsewhere in the function, but in this region, that's the minimum. That's called a local or a relative minimum. Whereas if it's the lowest point of the entire function, that's called an absolute minimum. Now, the rest of this is work for you to do. I'd like to clarify one piece of the directions. I don't think this was written as clearly as it could have been. This is the top of the second to last page. It says, write each equation explicitly in terms of x. What do you think that means? That's what I was thinking, is that x equals, but I think what they're really saying is write it as y in terms of x. So in other words, in this case, we'd subtract x and we'd get negative 3 halves y equals negative x minus 12. And we'd multiply both sides by negative 2/3 to get y is equal to positive 2/3 x plus 24 is 8. So that is solved for y in terms of x. In other words, there is no other place with y over here. You'll notice that in this homework packet, there are some things that are circled and they say HPC. That's because these are problems that are a little bit harder. I'm not assigning them to my regular pre-calc students, even for this little review thing that everybody's doing. So take a look for a second with your neighbor and see how you might solve this one. To solve it in terms of x, y in terms of x. Go. How we doing? How many people got it? It's a weird one, isn't it? This one comes up a lot in pre-calc. I will definitely show you this now and in other times. If we want y's to be alone on the left, then let's get everything that has a y in it over there. So we've got 3xy minus y. Let's move the x away, negative x minus 6. Now, the problem is I need this 3x out of the way. There is a y here, but it's being multiplied by all these. And there's a y here, and we see it as being subtracted. But could we also visualize this as 3xy minus 1 times y equals negative x minus 6? You guys agree that's the same thing? Now I can see that y is being multiplied by this and being multiplied by this. So I can factor that y out. And now if I want to solve for y, what do I do? Divide by 3x minus 1. And I get y is equal to negative x minus 6 over 3x minus 1. And that is solved explicitly in terms of x. But I would do one more thing to this. Anybody else see what they would do? 1/3. No, you cannot cancel that x because it's not also being multiplied by the 6 and negative 1. But I don't like having a negative sign here next to the lead coefficient. So what I'm going to do is I'm going to actually factor out a negative on top. And to cancel it, I'm going to factor out a negative 1 on the bottom. And so those negative 1s would cancel. And I'm left with x plus 6. But instead of writing negative 3x plus 1, I'm going to write that as 1 minus 3x. It's not just for fun. It is a form of simplification. You shouldn't have a negative on top. If this had been negative x plus 6, you could have swapped that, made it 6 minus x. That would have been okay. But you shouldn't have both of these terms negative. You'll get faster with that. What you'll do is you'll just quickly say, okay, those are both negative, so I'll turn them both positive and flip this around to make it 1 minus 3x. That shows up often enough that you'll do that. Okay, so you've got the rest of this class, and this is your homework to finish this up. I'm going to be compiling the answer key, posting the answer key. I expect you to check your answers and make sure you're right.
We gotta do this.